Alright, so today what we are going to look at is a few aspects of the problem of representing signal processing algorithms. Primarily what we are going to do is look at it from the point of view that how do I represent the algorithm, or how do I visualize it in some way that will help me towards implementing it in hardware. Okay.
So we'll take some examples to basically understand that better. What exactly is it that we have in mind?
To start with, as you are probably aware, any signal processing algorithm, the most fundamental form of representing it in some ways is the equation that defines it, right? So what do we mean by the equation? Examples of this.
What I'm going to do is basically take two running examples and basically look at them in all the different forms by which they can be represented.
So the first example that we are going to look at is an IIR filter. The equation that defines an IIR filter is y of n equals, well, this is one example of an IIR filter. This is not a general IIR filter, but this is one example, right? So essentially all that it's saying is you have some input x of n, sampled data, you are generating some output y of n, and a delayed version of that output y of n minus 1 is multiplied by some constant coefficient a and added to x of n, okay. So this is the equation that defines an IIR filter, one particular example of an IIR filter, assuming that a is a constant, okay. The second example that we will look at is an FIR filter. Over here y of n does not depend on previous values of y of n, but it does depend on other values of x of n. So for example, this could be one example of what we are looking at as far as an FIR filter, a finite impulse response filter, is concerned. The output depends on previous values of the input, but not on previous values of the output itself. There is no feedback, so to say, okay. So these are just two simple examples of what we would consider as DSP algorithms. There are of course many others. There are transforms, there are various kinds of filters, there are other compression, comparison, the quantization, various different kinds of algorithms that would qualify as signal processing. But these are just two examples that we are going to use in order to demonstrate the ideas behind the different representations. So the equation in some sense is the most fundamental, right? All that it's saying is you have x of n, some samples, you are doing some computation with them, and you are generating output samples y of n, okay. It does not say anything about how x of n is represented. It does not say you need so many bits, or you are going to use this kind of hardware, or these registers, or this clock period. Nothing of the sort comes into the equation, okay. The assumption is that these are just real valued numbers or complex valued numbers, as the case may be, right, with whatever precision is required in order to actually implement the functionality that you need, okay. Alright, so what do we do with this? When we are moving towards a hardware implementation, there are a few different kinds of visualizations or representations that we can use that help us to understand this a little better, right. And these examples are simple enough that we can straight away jump to something that is called the block diagram, or a block level architecture, right. The idea of a block diagram is simply this. All that it's saying is you assume that you are almost drawing it like a circuit diagram, okay, but using certain kinds of blocks with specific shapes in order to represent certain kinds of functionality, right. An example of what the IIR filter would look like, right, we had the equation for it, which was y of n equals a times y of n minus 1 plus x of n, okay. The equation for that could be considered something like this. This wire, this arrow that I have drawn over here represents y of n. What I want is one sample delayed version of that, I use this rectangle to indicate that it is some kind of a register or some hardware that can basically result in a one sample delay. Okay. That in turn gets multiplied. So I put a box with a cross sign in to indicate multiplication, and I indicate the coefficient of multiplication by the side of that, and this value gets added to another input which is x of n. Okay. So what we have done over here is we have certain blocks. These are functional blocks, and we have the wires that are essentially drawn as sort of circuit level connections between them, right. So you can sort of instantly recognize that this is very close to a hardware representation. This is directly sort of saying this is how the hardware will look. Okay. This is in fact potentially, if I had these blocks, if I had a register, if I had a multiplier, an adder and so on, I could directly implement this in hardware by wiring this up together on a circuit board. Okay. What would the FIR filter look like for this? I would have my input x of n. I need some kind of hardware that will generate two delayed samples. I am essentially looking at it as a shift register, right. So that what I have over here will be x of n minus 1, and what I have here will be x of n minus 2. Okay. Multiply each of them by the corresponding coefficients, this one by a, this one by b, and this one by c, and add. To get y of n at the output, right. Once again I have a whole bunch of hardware blocks, right, and the connections between them. Okay. Why did I choose these particular hardware blocks? It's based on some kind of an idea I have of how the functionality could be implemented, right. And one implicit assumption which we normally don't even think about over here is the fact that I have automatically assumed that A, I can add only two numbers at a given time. Okay, that's why I have two input adders. And B, I have already made the assumption that I am going to add A x of n plus B x of n minus 1 before adding the result to C x of n minus 2. Okay. Does this impact my final hardware architecture, how fast it will run, etc.? It could potentially, right. So the thing to understand over here is the original equation did not have that assumption. It did not say in which order you are going to do the addition, right. But the block diagram has already resulted in sort of enforcing part of an assumption over there. So what we will see is all the different kinds of representations that we have are ultimately going to impose some kind of restrictions on, or some kind of assumptions on the way that we implement things, right, and that in turn will affect what kind of information we can derive from those representations. Okay. So the block diagram is one, it's a very common one. In almost any signal processing book you will come across these kind of block diagram representations, right. All that the block diagram is saying is this is the equation, this is how you could implement it if you had hardware blocks that did all of these things. Okay. Another variant of a block diagram is something that is called a signal flow graph. And this is something that is more specific to linear time invariant signal processing systems. Okay. Over here what we say is, I will have, for example, yeah, once again, if this is the y, yeah, okay. This usually is used to represent the signal flow, and the Z transform domain is used to represent the signals, right. The Z inverse then represents one sample delay. A Z inverse, when it is appended to an arc like this, essentially means that any signal that is going across that arrow, that arc, gets multiplied by A into Z inverse. The A is a constant scalar, Z inverse indicates one sample delay. Okay, which means basically that we could eventually come up with this. And also any time that there is a junction, this indicates addition, and this is a branch which basically indicates a sort of splitting of the signal. It's not that half the signal goes here, half the signal goes there. It just means two copies of the signal, right? The same signal is sort of fanned out to two different places. Okay, so you have junctions and branches and these arcs. Okay, using this, essentially what we are saying is that the addition at that branch will basically tell us that the functionality that's being implemented by this is y of z equals x of z plus a z inverse y of z. Okay, or rearranging the terms, we can basically see that y of z equals x of z by 1 minus a z inverse. This is the z transform of the filter that's being implemented. Okay, the IIR filter, so we can directly derive it in this way, right? Superficially, and for the most part, it is very similar to the block diagram level architecture. There are like a couple of different properties in the analysis of these signal flow graphs. They are slightly more restricted in scope. There are certain things that can be represented as block diagrams that cannot be represented in signal flow graphs. But the benefit is, once you can represent a signal flow graph, there are certain kinds of analysis that are possible that may not always be possible on a block diagram, right? We'll get to that in a moment. Before that, let's see what the signal flow graph for the FIR filter would look like. Essentially what we are saying is, now the x would get multiplied by a z inverse over here and another z inverse over here, and from these branches I would have A, B and C coming over here. I have this structure, so that I have y of z, right? And in this case I can straight away write down that it's equal to A x of z plus B z inverse x of z plus C z power minus 2 x of z, right? So y of z is equal to A plus B z inverse plus C z power minus 2 x of z. Okay, so this is all the standard transform domain stuff that you are already familiar with, right? All that it's saying is the signal flow graph directly allows you to represent things in that manner and derive the results accordingly, derive the transfer function if you need. Okay. There is one important property or one useful property of a signal flow graph that can be useful in certain contexts. It is not universally applicable, but at least for certain kinds of signal flow graphs, if something can be represented as a signal flow graph, then you might be able to apply this transformation to the structure, which basically potentially in certain cases could give you an alternative insight to what the architecture can look like. Okay, and that essentially relates to the fact that there is a theorem which says that if you can switch all the inputs, switch the directions of every arc in the signal flow graph, right, and replace junctions by branches and branches by junctions and swap the input and output, you will get the same functionality. Okay, so what exactly does that mean? Let's see what it would imply if I was to reverse all the arcs in this diagram, right? This top arc would go like this, direction of this z inverse reverses, direction of this z inverse reverses. Okay, this point, which was a branch, becomes a junction over here, where this A arrow has been reversed, and this junction becomes a branch over here. and of course I need to reverse the, or rather swap the positions of input, so that the input now x of z is over here and y of z is over here. Okay. So the theorem essentially says that these two graphs are fundamentally equivalent. They are going to give you exactly the same behavior. Okay. Now, why would something like this be useful? So in other words, what we have done is we have managed to invert the direction of all the edges, right? And we have got another signal flow graph which looks superficially the same. Okay, it looks very similar to what we started out with, but there are, or at least there is one subtle difference which becomes more evident when we look at the equivalent block diagram representation for this particular signal flow graph. Okay, so what I am going to do is just draw the block diagrams corresponding to both of these. This one essentially corresponds to what I drew earlier, which is x here, y here, a, b, c. Okay. The one at the bottom, I am once again going to draw it similarly to the top one, in the sense that x will be on the left, y will be on the right. Okay. But the connectivity will be as seen by the signal flow graph on the bottom. Okay. So with this picture in mind, is there anything that you can notice over here that tells you whether one is better than the other in some way? What's the primary difference that you can make out between both of these? So the shifting, the order in which you do the shifting, whether it's before the multiplication or after the multiplication, or rather, what are you multiplying? Are you multiplying the results of the shift, or are you and then adding, or are you multiplying something and then adding and shifting in some other strange way, right? The important point, the one that ultimately becomes relevant from a hardware point of view, can be seen in the context of something that we will be looking at in a bit more detail later, but you already know it. It's something called the critical path of the circuit. Okay. So what is the critical path in a digital circuit? It's basically the longest combinational logic path through a circuit. Okay. And in this case, if we look at it, the longest combinational path is essentially going to be like this, right? The multiplier followed by two adders. Okay. Now that's because it's a 3-tap filter. If it had been a 10-tap filter, it would have been a multiplier followed by 9 adders. Okay. In other words, the critical path would essentially have all those additions would end up being on the critical path. Now, should you really do them as a chain of 9 adders, or can you do them in certain other ways by creating some kind of a tree structure and so on? Yeah, there are a lot of optimizations you can do. But at the end of the day, there are a whole lot of adders that are going to end up in your critical path. Whereas over here, the critical path is essentially going to be always 1 multiply 1 add. Okay. Fundamentally, it has been changed in such a way that after every adder there is a register. Okay. So the output of the addition basically goes into a register, and in that way effectively what we are saying is that no matter how many taps this filter has, the critical path is always going to be restricted to 1 multiply and 1 add. Okay. So from that point of view, at least, what is the basic critical path that you will get if you straight away look for a hardware implementation of the circuit? It looks as though this second implementation that we have shown over here is probably better. Okay. Is there a catch? What's the problem that you can think of in this context? Why do you need a big shifter? So that's one very good point, right? Essentially what is being said is, the x over here will be some number of bits, right? If this is some n bits, then this will also be n bits, this will also be n bits, right? But the moment I multiply an n bit value with something else, the number of bits that I actually need in order to represent the result is more than n. right? If I take two n bit numbers and multiply them, strictly speaking, I need two n bits in order to represent the result. Okay. So in this case, what is happening is the multiplication is happening right here. This is n bits, but this is greater than n bits after the multiplier. So the shifters now need to be bigger or wider. Okay, that's one problem. I may be able to get around that by sort of saying I'll use a fixed point representation, and after the fixed point, I know that it's fixed point anyway, so what I'm going to do at the end of the day is I'll multiply two, let's say 8.8 numbers, and I will round the result off also to an 8.8 value. Okay, so if I do something of that sort, I may be able to get around this shifting problem. Okay, but nevertheless it is there, it is something that I'll have to deal with. There is another problem that I could potentially encounter over here, which is related to essentially something called the fan out. Okay, can you see if there is any problem with regard to the fan out that I need for signals in either one of the designs? In the second architecture, this x of n, this input, is now driving three multipliers, a, b and c. Whereas over here, x is getting multiplied by a, the output of that first register is multiplied by b, and the output of the second register is multiplied by c. So in the first architecture, which by the way is called the direct form 1 architecture, right, I never have to worry about large fan out. The signal is always going through a register, and the output of the register is then going to a multiplier and then also being branched out somewhere else. Right, but direct form 2 on the other hand, which is the transposed architecture, which has basically been obtained by taking the signal flow graph and transposing it or inverting it, right, as we discussed, that has a problem with so called broadcast. Right. So x needs to be broadcast, meaning that at the same time it has to be sent to multiple different multipliers, right, a, b and c, and that could either result in a high fan out, therefore high capacitance, therefore high delay, or it could result in something that requires like accessing a particular memory location multiple times. Either one of them could potentially be a problem. Okay, especially the fan out part of it is more likely to be a problem from a hardware point of view. Okay, so bottom line is you can't straight away say one or the other architecture is better, right? This is sort of Pareto optimality as you can think about it, right? All that it's saying over here is I have different implementations. One of them is better from a critical path point of view, the other one is better from the broadcast as well as the number of bits required for the registers. Okay, so why did we go through all of this? Because the important thing that we needed to keep in mind over here is the signal flow graph representation effectively allows us to come up with these two different architectures for a given filter.